All right, here we are, and we finished up our invariant-based models, and now we're going to go to fiber-based models. And in fact, it's still sort of an invariant-based model, but it's based on the idea of fiber stretching. And the beauty of invariant-based models is that they're very easy to construct. But the problem with them is that they lose the fine detail. You can't really talk about what's going on at a fiber level in the same way that you'd like to. So I have this slide. It's called a bit of a stretch. We know that I4 is the stretch in the direction of a fiber. We used it to produce fiber invariance. And we're going to do that again today a lot. So we're going to use a lot of I4. So let's remember that I4 is the stretch of a vector pointing in the direction of some population of fibers. In this case, I point them in direction n. Okay? And this is a very popular choice, particularly the early work of Fung, some of Lanier's work, and then more recently Humphrey and Holzapfel. We see strain energies that look like a neo-Hookean contribution. So this is I1, this is the trace of the right Cauchy-Green tensor C, and a fiber contribution that has an I4 in it. Right? And it's an exponential because that seems to describe data well. Okay? And this works really well if you have one or two groups of fibers, but what do you do if you have more? J. Humphrey uses a 4-fiber family model, and we're going to talk more about that next time. So he has 4 K1 values and 4 expressions like this. Okay? As a general rule, if you think all of your fibers are the same, but just pointing in different directions, then K2 shouldn't change because it describes the behavior of a single fiber. K1 changes because it captures how the fibers are aligned, or you could have a separate prefactor that captures how the fibers are aligned. Okay? So what do we do if we have a continuous distribution of fibers? So we have fibers pointing in all directions. We certainly can't make an infinite number of expressions. So what we're going to do is we're going to say, well, we could just discretize the distribution and calculate a term like this for each direction. So we could say there are 20 bins in my histogram of alignment, and I'm going to make 20 of those terms, like that one with the purple arrow pointing to it, and then I'm going to add them up. Michael Sachs does this. Gerhard Holzapfel has started doing it some. It gets very expensive computationally. It's just not a convenient way to do the problem. All right? So a second option is to recognize that this is really an integral. All right? If we have an infinite number of these with some infinitely small probability of each one, but the probability is distributed, we are integrating from 0 to pi if we're in 2D. So fibers can point this way up to here, and that's it. You could do minus pi 2 if you wanted to, or you could argue that it's symmetric. Oh, sorry, 0 to pi, so it goes all the way, so we're good. Of some probability of a fiber being in that direction. And p then is a probability distribution function. So if all the fibers were aligned this way, p would be a delta function aligned in the one direction, or theta equals 0. If it were this way, p would be a delta function of theta equals pi over 2. And if they were distributed uniformly, p would just be equal to 1 over pi. So then the integral of p d theta would be 1, and it would be uniform. So we can pick whatever distribution we want. And this is very attractive because there are a lot of good experimental techniques to measure fiber orientation distributions. So here's my integral again. Now we have to evaluate this integral. And that's hard, right? So there are a couple of ways to do it. One way is to do it numerically. And that's a little better than a big summation, but not much. Effectively, you're doing the same thing. You're breaking this up into little parts, calculating individual integrals, and adding them up. There are a couple of special cases where you can evaluate the integral analytically, which is really nice. If your p has the right form, then this integral has a closed analytical form, and you can just evaluate it, and then you have a strain energy function that you can use. I actually wrote a paper on an example of that some years back. And then finally, I want to spend a little time today talking about a method developed by Gasser-Ogden and Holzapfel. It's usually called the HGO method, the Holzapfel-Gasser-Ogden model. I think Holzapfel cares the most about having his initial first, so that's why he's first. And so what they did was they said, well, let's introduce a new structure tensor, which we'll call H, and it is the integral of aij p d theta. So it says for any given direction, I can define a vector in that direction, that's A. So if it were in the flat direction, A would be just 1, 0, 0. If it's up here, it would be 0, 1, 0. And if it were at a 45-degree angle, it would be 1 over square root of 2, 1 over square root of 2, 0, and so on. And P of theta is the probability distribution function for finding a fiber in that direction. Okay. So this is nice because you can see this is going to be I4-like, right? Because it's got that AIAJ in it. So here's my equation again. And if I say AIAJ, right, because if I multiplied AIAJ by C, I would get I4. And so Gathner suggested a new invariant, which is Hij times Cij. So this is the double contraction of H with C, and he's using the deviatoric invariant. But we're going to make things incompressible so that the J doesn't really matter. And so you see, this is like I4. But it's not just I4. If I bring this up, it's Cij, since Cij does not depend on the direction of your fiber, Cij can go inside this integral. It's the integral of Cij Aiaj times P. So it's essentially, you say, I'm going to take every fiber direction, I'm going to calculate what I4 is for a fiber in that direction, and then I'm going to take a weighted average of the probabilities. So in essence, it's a weighted average of the squared fiber stretch over all possible fiber directions. That's it. A very nice thing. And this is their real coup. And this is actually my last slide. This is a relatively short lecture, but it's very dense. It's a lot of things to think about. Was to say, well, this is what I want is the integral of the exponential of I4 weighted by P of theta. Instead, I'm going to take the exponential of the weighted I4 integral, which he called E, and I'm going to use that instead. Now, this is obviously cheating. Right? Because the integral of a nonlinear function is not the same thing as that function applied to an integral. Right? Because they don't, the exponential does not distribute over sums. But it makes the math much, much faster. Because you can calculate E really fast, and then you don't have to redo all that integrating because you already calculated H, which is the thing with the integral in it. You just double contract it with C to get E, and then you have this nice formula. And so it's really easy to use. And one might argue, but it's cheating. And then I think the counter argument to that is, well, maybe it is. But there's really nothing in the physics that says it has to be an exponential of something squared anyway. And so maybe this model isn't the same mathematically as the other model, but who's to say that it's really worse? And I think that's a very sound argument. So I would be very comfortable using an HGO model in my own work. I generally don't because I don't do that type of problem, but I think it's a very good model. And so I'm supportive of it, and I wanted you to see it. So we're going to play with things a little bit. We're actually going to come back next video, and I'm going to work through some more stuff with the 4-fiber family model and the HGO model, and then we'll go. But for now, we're just going to do some quick calculations, and I will see you soon. Bye-bye. Hi. So welcome back. And our problem for today is using the HGO model. I picked that because it's a nice one and it has a fairly easy sort of internal calculation. And what we want to do is calculate Hij for a distribution with two fibers, one at plus 30 degrees and one at minus 30 degrees, and those two populations are equally likely. Okay? So remember, H is the integral of Aij P of theta d theta over all possible thetas. And in this case, there are only two possibilities, and they each have a possibility of a half, which would be 1/2 times a delta function. So in this case, H is going to be equal to 1/2 times AI AJ, I'll write it like this, evaluated at theta equals plus 30, plus 1/2 AI AJ, evaluated at theta equals minus 30. Right? And fortunately for us, we know what those A's are because we did them in our last assignment. I very conveniently picked the same thing, and I'll just write them over here in the corner. So they're exactly the same except there's a plus and a minus on the 1/2, okay? So now I'm going to calculate these. Let's start with this one. So AIAJ is equal to, all right, the 1, 1 component is A1 times A1, which is, and remember, the subscripts are indices, not which A it is. These are both for the 30-degree A over here. These are just x1, x2, x3 indices. So A1 is square root of 3 over 2, so A1 times A1 is 3/4. The 1, 2 component is square root of 3 over 2 times 1/2. And anything with a 3 in it is going to be a 0 because of that 0. This is the 2, 1 component, so it's A2 times A1, and you can see that this has to be symmetric. It has to be symmetric because multiplication is commutative. So A1 times A2 is exactly the same as A2 times A1. This is A2 times A2, which is which is a 4th. That's a very strange looking 4. I'll make a more 4 looking 4. Actually is a 4. And then a 0, and then 0, 0, 0. So this is A1, this is AI AJ in the plus 30 case. In the minus 30 case, AI AJ, it's exactly the same except we have a minus here. So So 1, 1 is the same because it's root 3 over 2 times root 3 over 2. 2, 2 is the same because the 2 minuses cancel out, but now we have minuses here. Okay? So now if we take these two and we multiply them by 1/2 and add them, you can see what's going to happen. The off-diagonal terms are going to cancel out, and the on-diagonal terms are the same, so when you multiply them both by 1/2 and add them, you're going to get the same thing. So we'll end up with that. So that's what H turns out to be. Okay? And I want to make a couple comments before we finish because there are a couple things that are important to observe. The first is, in this simple example, H worked out to have only diagonal components. That is by no means necessary. And for different choices of things, we would not get all diagonal components. The obvious case would be if all the fibers were in the plus 30 direction, H would have just been this, right? So, and if we had more fibers, if one of the two populations had been bigger than the other, then these would not have been weighted equally, and these would not have canceled out. So in this case, the net effect of the two, the sum of the two is to eliminate off-diagonal terms. Because if you pull it in the one direction, what that means is these fibers, if you're on this side, are trying to pull you down, but these fibers are trying to pull you up, and the net is 0. So a pull in the one direction generates no pull in the two direction, and vice versa. So that's why it's diagonal. The second thing you'll notice, and I think this is just important because we don't always think about it, this matrix, what I would call an orientation tensor, it captures a lot about it, but it also misses a lot of fine detail. We have integrated out the fine detail. You will notice that if I had, I'll just go in here so I can draw a picture. I'm going to show you two fiber populations now. There's this one, which is the one we just analyzed. And here's another one. You can tell it's different because I'm going to make it a different color. Whoops. Watch out for the flying towel. Oh, I don't want to do it that way. I'm going to fix this just a second. Fortunately, you have nothing else to do but watch me. So here we are. Okay. I'm going to do this. I'm going to draw my axes. I'll draw my axes in orange. But I'm going to draw my fiber population in blue. Okay. So there are 3 times, and I just drew them a little off the axes so you can see them. There are only horizontal and vertical, and there are 3 times as many going horizontally as there are vertically. All right? If I did this, I would get 1, 0, 0 for AA for these guys, and 0, 1, 0 for these. And when I weighted them by this 3-to-1 factor, I would get the exact same H. These two fiber populations are exactly the same in terms of this model. All right? If you pull on it this way, you get roughly 3 times as much fiber stretch as if you pull on it this way. All right? And that's very good, that's very effective. But you should be aware that we are losing some information when we go to this integral representation. So that's all I wanted to say, and we will talk more about fibers in class. Have a good night.